Hello, audible?
Audible, sir.
Please ask me. Okay, we're discussing the transformer questions, correct? Hello, dear. Yes, please, audible?
Yes, sir.
So here, these are the all new question which was asked in this transformer chapter. Okay, please read this and go through this. Okay, mostly recently asked questions. These are the okay. Like here, first, which is recently asked, correct? They ask, what is the leakage flux as it applies to the iron core transformer? How it taken into account in analysis of the transformer? In analysis of the performance of transformer performance, I think. Okay. Yes. Discuss the magnetic leakage. Magnetic leakage. Why it is important? In December, it is asked why it is important. Yes, actually, this is the recent is asked in
November month.
Third is asked in 12th, means December month. This is in November. Okay. What is the purpose? Yes. Yes. What is the leakage flux as it applies to the iron core transformer? How it is taken into account? How it is taken into account in the here. Okay, actually it is in the analysis of the transformer only. Okay. So see, you means analysis of transformer. We take the test the performance. What is the analysis parameter? Efficiency and voltage regulation. Correct. Same question is third also. Why it is important to maintain the high efficiency, okay, and value of voltage regulation and low value of voltage regulation. So if leakage flux is low, your voltage regulation is leakage reactance is low, then voltage regulation is good. Good means low value. Okay, dear. Yesterday I explained leakage flux. Then again another also question was asked in related to this leakage. Second, discuss the magnetic leakage in transformer. Indicate how it is value may be kept down. Means how we reduce this leakage flux. Leakage flux means leakage reactance. Correct. Then show by mean vector diagram. You have to show with vector diagram how this affect the voltage regulation. Okay. So actually this first question part A, and this third, okay, and the second. The second and first is same question like, correct. Okay, dear, and I will explain you because leakage flux means leakage reactance. If leakage flux is high, leakage reactance is more. More leakage reactance means high impedance, total equivalent impedance. Then there is a voltage drop. Okay. So this correct. So mostly we collect this already these questions here. Now please. Let us we start from actually we yesterday discussed the vector diagram. So this fourth part A with add-on delta star diagram. You have to show the star delta connection and write the basic equation of line voltage and line current. from which we can derive the star delta or delta star conversion. So in the first question only you draw the vector diagram and you write the star delta connection, balance star delta connection, and write the equation. Okay. So let us this fourth one we first take. Okay, TH.
Excuse me, sir.
Yeah.
सर लास्ट 4 मंथ का सर आपने सभी न्यूमेरिकल्स के आंसर है ना ग्रुप में डाल रखे हैं और दिसंबर का पार्ट सेक्शन 2 भी है सर टोटल। तो जो दिसंबर में क्वेश्चन आया था सर सेक्शन फर्स्ट में बोथ रेस्ट का, तो सर सेक्शन फर्स्ट का भी आप आंसर डाल सकते हो सर।
उसमें वो डिजाइन पैरामीटर पहुंच रहा था ना, वो लाइक मोटर ओवरलोड, हीटर मोटर ओवरलोड एंड
केबल प्रोटेक्शन एंड प्रोटेक्शन मेन स्विच बोर्ड सर।
So actually if you have like in SIP data sheet or catalog some that is have a short circuit, we have a circuit breaker that provide main switchboard mein what is the protection. Circuit breaker like under voltage, over current, short circuit, correct?
Single
Then
phase
for motor we have a starter. So there is a overload relay we provide that, and other is cable protection. So we require a armored or XLP insulated with PVC inner sheet, outer sheet. What is the, so their technical specification you have to write for all three things. Okay. I will find out in this okay within 2-3 days. Actually he is asking for 3.3 kV particular, correct?
Yes sir.
What is their ratings for that 3.3 kV system, like main switchboard and your motor, overload relay and cable? So you have to decide the cable size, what is the motor, kilowatt rating is not given. What is the kilowatt rating of motor for 3.3 kV? Yeah?
Yes sir.
How much kV? Kilowatt?
3.3 kV sir.
3.3 kV is the voltage. What is the kilowatt rating of motor? Okay, you just check what is the kilowatt. If we know the motor rating, kilowatt rating or HP rating, then we can calculate what is the starting current based on the motor full load current and the starting current. We have to select the switching means starter component, means rating of your fuse or MCCB, then your overload relay. Okay, correct?
Yes sir. And sir November also one question theory sir I उसका आंसर नहीं मिला सर। सेक्शन फर्स्ट में सेकंड का एक पूछा था फ्रीक्वेंसी रिस्पांस का ट्रांजिस्टर एम्पलीफायर।
ओके ठीक है, I will put search and put. Actually myself now I collect this questions chapter wise, then
Okay,
I
sir.
will search the question this answers.
Sir numerical no problem sir, numerical I have answered 12 months sir, लेकिन theory part section first second is very difficult sir Pandu. Some question.
Yes.
Okay sir.
Yeah. Actually I have collected that is in electronics, no?
Yes sir, electronics part.
These are the questions I have collected here. Okay. Red mark. List the two factor of cause the distortion of the frequency response of transistor. You are talking about this, no? Explain with how each factor affect the performance of amplifier and portion of frequency range it will be affected. Explain what is the meant by the terms waveform, frequency and average value. It is okay. This question we have carried out. Here this SCR, okay. Now this common emitter amplifier you can draw with the biasing resistance and coupling and decoupling capacitors, and you explain this diagram. Fourth, you can search it is easily in your some actually signal electronics you take like VK Mehta one book is there, basic I will put, okay, not issue. And this amplifier circuit, oscillator and rectifier. Then this Zener diode, already I put some notes here.
Yes, sir. Zener diode got it.
Rejection diode, and then this rectifier question already we put. Then this amplifier and frequency range. Also. Fourth one, here actually, you know, in star, balance star, perfect. This is the star connection, okay. There is a delta, this is star. So here it is a delta connection. So here, first you understand the terms of three phase. There is a line voltage, then phase voltage, okay, then you write line current and phase current. What is the meaning of this? Actually, voltage, line voltage, it is between, when we measure between any two lines, like this is line 1, line 2, line 3. So between any two phases or lines, okay? Phases. So now phase voltage between this, you know, phase voltage here, the voltage between line and this neutral point with respect to, or the voltage across the phase, each phase winding, because there is a three phase now, 1, 2, 3, R, Y, B. So the voltage across each winding, that is called phase voltage, and voltage between two lines, that is called line voltage. So this is the difference, okay? So this is the voltage. Phase voltage means voltage across each winding, each phase winding, okay? Got it there? Then line current, which is flow through line, any line here. So this is the line current, okay? line current. These are the line current. Now, phase current means flowing through each coil or winding, phase winding. See here, the current in the coil itself here from this, that is the phase current. This is phase current. So actually for star, for this star here, you know, if one can calculate line voltage is √3 times of phase voltage. Okay, correct. But line current equals to phase current only. They are saying. Okay, this is for star connection, balance star connection. For delta, see here, the voltage here between these two lines, that is line voltage, line 1, line 2, line 3. Now, if we measure the voltage across this coil, this is the phase voltage, so it is the same here. But here, the current in each phase, see, suppose this is the current here, this is current here, this is here. Now here, you know, this is the line current. Correct. Here, this is the phase. Here it is a phase current, but this is line current. You know, there is a difference in these two currents, because it is a node. Some part is going here. This is suppose incoming, then it divide here. So means here for delta, line voltage equals to phase voltage, but line current equals to √3 times of phase current. This is the basic equation. Okay, this much only you write. Okay. Now we come to the part B. Okay, dear. This 4 part B. Here it is 230 by 115 volt. Single phase. Transformer. Is supplied with a load of, so there is a load current on secondary. That is load current means it is a secondary current. Okay. Okay, that is I2. Load side. Suppose this is your transformer. So it is given I2. I2 equals to 5 ampere. 8 power factor is also given. Okay. Cos phi 2. 0.2 sorry, 86. 0.86, sorry, 0.86 lagging power factor. It is 5 ampere. Okay, dear. Now from this we can calculate phi 2 equals to cos inverse of 0.86. What is the value? This angle will come. You use the calculator. Okay. Cos inverse 0.86. 30, 30.68 degree. Then if you calculate the value of sin phi 2, sine of this answer, you get a 0.51. Okay. 0.3, like this. Okay, dear. This is the load. At no load. At load. Secondary current. Huh? Now at no load. No load, there is a I naught current. No load current. It is given 0.2 ampere at 0.208. So it is 0.2 ampere at cos I naught, no load power factor. Okay. Now at no load secondary, it is not a secondary current and secondary power factor. Okay. At no load means your secondary is open. This is your primary side. Zero power means power factor at no load. That is very low. As yesterday I told. Power factor is low means angle will be large. If you calculate cos phi inverse, cos phi naught equals to 0.208, then what is the value?
$78.
0.99, and so we can write 78. Yeah. Then sine of this G. So we can write na sine phi naught. It comes 0.978. Okay, dear. Now we can calculate two component of I naught. That is I naught cos phi naught plus I naught sin phi naught. Okay. This is actually your this omega loss component. This is loss component. Okay, and this is magnetizing current. It is 0.2 into 0.208. This value will be, and this is 0.2 into 0.978. Okay. Right here, this comes 0.1956 ampere, and this is this 0.0416. These are the current. Okay. Okay. Now, sorry. Now you have to draw this phasor diagram. Okay. Here. Suppose this is your voltage, primary side phasor voltage. This is your V1. Now suppose this is your horizontal axis. See, this no load current. No load current is lag by angle. How much? What is the angle? 78 degree. Means it is close to 90, like this here. So this is your I naught. Now it has a two component here and here. Okay. This is I naught because this angle is phi naught, correct? So it is I naught sin phi naught. This is I naught cos phi naught. Okay, please remember. Okay, so this two component we calculate now. This is your I omega, this is your I mu. Okay, you know this is magnetizing current. It produces the flux in the core, magnetic flux. Please, this is produce the magnetic flux. Due to this flux, there is a voltage are induced in self-induced EMF in primary and in secondary. Okay, so suppose it is as per your data, this is E2 and this is E1. Okay, let us here we neglect the impedance. Okay, then your this equals to V2. This equals to, it is minus E1 means, okay, if we neglect the voltage drop in primary and secondary, so it is minus E1. Okay, sorry, opposite, because it is downside, na, E1 equals to this. Now secondary load current, when see, suppose this is your transformer, this is your secondary, there is a load. Now this is the cos phi 2, this is I2. Okay, here this transformer take here I1 then. Okay, at load I1. Then there is a, here it is a secondary power factor V2, but here it is E2. So here we neglect the voltage drop, then these are equal. Here it is also V1 or E1, here induced voltage. But my dear, here we calculate, he is asking I1 and cos phi 1 overall power factor, primary power factor. This secondary power factor is known, and this current is given. So means your I2 is lag with, your I2 is lag with V2 because it is at lagging power factor, this 30-degree angle. This is your phi 2. This is I2. Now as refer to primary side, hello, this is, now this angle is same phi 2, yeah, but this is your I2 days. As refer to primary side, what is this value? It is KI2. So now we calculate turn ratio. What is the turn ratio? Sorry. K equals to E2 by E1 or V2 by V1. So it is 115 by 230, correct? What is the value will come? Point 0.5. Okay. Correct na? So value is correct na? Okay. It asked in November na? No.
October, sir.
October, yeah. Hmm. 115. Okay. So see, 0.5, then this current will be, hello? This current become
2.5.
5 into load current is 5, correct? 2.5 ampere, half हो जाएगी. Then you know now this is primary voltage. You know, as I told, at load condition, if we see in equivalent circuit, correct na? See, suppose this is your this is your magnetizing branch here. Okay, this is your load side. secondary side. This here we apply the voltage V1. Okay. Then there is a I1 current. At this node, there is a I0 no load current, and here it is I2 dash as referred to. Then what is the primary current total? This is a vector sum of these two. Sum of the, but these are not, it is not an algebraic sum. We cannot just add I0 means 0.02 plus this 0.25. No, because they are out of phase, no? That's why we do the vector sum. Okay. Got it? So this is your primary current. So my dear, if you know this two vector, suppose there is a vector P and vector Q. Then if we know the theta between these two, angle between these two, theta, then resultant one we can calculate this R vector sum, R. Okay. This is P square plus Q square plus twice PQ cos theta. This is R equals to, and E square, R square equals to, then we put a root. This will give the resultant. But actually here na, in this question, hello, angle between these two vector, here is a two vector na, this I0, this is your I0. Okay, so this angle is also not available here between this. ये इसको हटा देते हैं. See, this is the vector sum. Okay, this is the okay. So now, if we calculate na the vector sum of these two, this and this will give you I1. This is your I1. Okay, this is your I1. Okay, dear, I1. Now, this phase difference between B1 and I1, it is phi1. Okay. So how in this case, this formula is not apply, because we do not know the angle between these two, I2 dash and I0. I2 dash and this I0, okay, we not have a phase angle. Then this is not applicable. Now other method is how we can calculate. Very simple. We resolve this vector. Suppose number of vectors are there. Suppose this is the two vectors. Sorry. Okay. Suppose there is a number of vectors are there, like this. How we calculate their sum? Actually, we resolve this all vector into horizontal and vertical. We take a component of this. Like if we should know the angle like this, then we calculate their component, vertical and horizontal. Okay. Then finally we get a total vertical and total horizontal. Okay. Then their sum we can calculate like this. Okay. This will give the sum. This is total, this is total. Then this will be resultant. Okay. So same we apply here. Similar to I0, na, we also calculate the component, two component of this I2 days also. Okay. Here and here. Yeah, this two component of this here also. Correct here. So similar like I0, we calculate the vector. I2 days we calculate. Okay. We know secondary load current as refers to primary side, primary side. That is I2 dash. Equals to KI2. or it is 0.5 into 5, 2.5 ampere. Okay. Now we calculated two component. When we resolve this, we also calculate two component of I2 dash. That is I2 dash cos phi2, I2 dash sin phi2. Okay. I2 is dash is 2.5. 2.5 into power factor is 0.86, correct na? Here it is 2.5 into power factor, this cos, sin phi is sin phi 2. Sin phi 2 is 0.51, 0.5102. What is this values will come?
Two 2.15.
2.15 ampere, and this is
1.27.
1.275. Okay. Now we calculate total horizontal component, means along x-axis you calculate x-axis. Hello my dear, here along this is x-axis, suppose this is x-axis, this is y-axis. So along x-axis means sine term, I naught sin phi naught plus I2 dash sin phi 2. Okay, so please write the values, and this will give you Ix total. It is I naught sine terms is 0.1956 plus sin phi 2 here also it is 1.275. So it comes plus 0.1956. It comes 1.471. Second, we calculate total vertical component, that is along y-axis. So that is Iy. Iy equals to I naught cos in cos terms, I2 dash cos phi 2. Okay. It comes here I naught cos phi 2 is this na 0.0416 plus here it is 2.15. Okay, this, my dear, it comes 2 2.2. Okay, 191 ampere. My dear, this we get na total. It means this is your IY, correct? This is your IX. This is IX. This is your IY. Then we calculate their vector sum. This will give you I1. So you know this is IY. You take this one. This is also IX, no? It is equals to this, huh? Okay. So now you take this angle, right? This is right triangle, no? This is you take it. This is your phi 1. Okay, phi 1. So you know this is your perpendicular. This is hypotenuse, I1. Okay. So now we can calculate the primary current, and you know along this axis there is a V1. This is B1. It means I1 V1. This is the phase difference phi 1. Okay. So here we can write the primary current. I1 equals to, this is Ix square plus Iy square. Okay, dear, so it is 1.47 whole square plus 2.19 whole square root 471. It comes 2.639. So generally, actually, you know, if you apply, see, some person then asks, sir, why he is asking primary current. Secondary given means I2 is given 5 ampere. Now he is asking I1. So see this is just we apply the turn ratio. Why we do this so much things? So my dear, this turn ratio, na, your I2 by I1 by I2 equals to your V2 by V1 equals to K. It means I2 equals to KI2. This is for ideal case. Ideal case. Here we neglect na actual mein. This is not a sorry. I2 equals to KI1. Na? Sorry, I1 equals to, and this is I1 equals to KI2. But it is not I1. In practically it is I2 dash by I2 equals to K. Okay, this is the correct. It is for ideal case or loss free transformer. Okay, if loss free, this is for ideal transformer or loss free. This is for practical. So actually, if you apply this, it will give you wrong value. What is the current will come? Only 2.5 amperes. But if we calculate by this process, it comes 2.64. Okay, higher than this. Correct now, because here when we calculate derive this turn ratio, we assume no load current, we neglect. Correct? No load current means actually I1 is the vector sum of I0 plus I2 days. So when we for ideal case, for this turn ratio, we neglect this. then your I1 become I2 dash. This we use, okay? Actually, it is not correct. This is the correct, okay? Understand? This is
तो ये प्राइमरी करंट I1 का फॉर्मूला कैसे डिराइव किया आपने?
which one? This?
हाँ yes sir.
This is Pythagoras theorem, my dear. Right angle.
Okay.
In any right angle triangle. This is your right angle triangle, no? Hypotenuse.
Okay, understood.
Okay, dear. So this is the question which was asked in your exam. Now there was in earlier in ETO exam. There is a question. See, this first question is same. Okay. This first question is also same. Okay, or in old they ask you this question, you know, in old exams, number of times this question, every alternate month they are asking. Same, okay? But here, actually, the no load power factor is not given, we have to calculate it. In this idea, I hint, see 100 kVA, this is the ratio, turn ratio, 2400. Single phase transformer has a no load current, I naught is given, okay? Core loss. So you know, my dear, in transformer, core losses are equals to no load input power, no load, because we do in no load test, no? Or open circuit test, no load, or open circuit power input, we consider as that appear as a total loss. Copper loss also there, negligible. Just we consider only core loss, okay? This. And this is equals to, if it is, we apply the rated. Now we say that, hello, when it HV side is energized at rated voltage and frequency. My dear, this is the condition for no load test. What is the condition for no load test? Okay, this we kept open secondary. Now it depends. We can perform on LV side also. Low voltage side. But okay, generally for better, we conduct on HV for correct value of loss. But if you not have available, it depends on your voltage source. If you have high voltage, then you can apply. So here we apply the 2400 volt. Okay, with the rated frequency 50 Hertz. Okay, rated voltage, rated frequency. This is the condition for no load test. Okay, because your iron loss depends on frequency and voltage. That's why we conduct on rated voltage and frequency. Please remember, so that it gives the correct value of core loss. So see, this take this much. So it is I1, I naught, cos phi naught. This is the power input to transformer. Now this equals to 700 watt. Means it is W naught, no load power input. Okay, it is W naught equals to this. Please. Now from this you calculate a cos phi naught equals to W naught by V1 I naught. Okay, so just you put this 700 divided by what it is, then 2400 into no load current is 0.64 I naught. So this will give, this is lagging power factor, very low. So it will give cos phi naught. Then phi naught you can calculate. Then sin phi naught. Okay. Now in second case he said that calculate the two component of no load current. So See, here is a step question also. When you calculate I naught, two component of I naught, I naught cos phi naught, I naught sin phi naught. You get a number because he is asked. Then if transformer is supply a load current of 40 ampere 0.8 degree, 0.8 lagging power factor. So here I2 is given 40 ampere. Then cos phi 2 is also 8 cos phi 2. Here power factor is given cos phi 2, that is 0.8 lagging. So it is cos phi 2. We can calculate phi 2 equals to cos inverse 0.8 and it comes 3686 like this. Then we calculate sin phi 2. It comes 0.6. Okay, 0.68 value. Same like here also you calculate sin phi naught, cos phi naught sin. Then these two values you get. Okay. Now then to turn ratio K equals to 240 by 2400. So it comes 1 by 10. 1 by 10, please. 110. Then you calculate I2 dash KI2. So it comes 4 ampere only because 14 into 1 by 10. Then to same like vector diagram you draw and you calculate I1 phi 1. Now again it is the same question, same pattern. Okay, like this. You have to calculate like this. Okay. Got it? Any doubt here, please? Hello?
Yes, sir. It is okay.
It is. Now this is okay. It may be asked again, we cannot say what they ask. There may be new questions. So you have to learn the pattern, not you. Actually, now you have to understand. Suppose new question is come, then you have to know how we solve. They change the values, they change. Suppose here it is not give the power factor, but in here they give the power factor. Okay. And here it is written, see, because ignore the leakage impedance. That's why we here not consider the impedances. Now next questions we talk here. No? Where is our questions? Here. Flow size efficiency, tomorrow we discuss. But today now we come to the voltage regulation. Okay. Correct? Okay, so already here now this is the here already we draw the equivalent circuit as referred to primary or as referred to secondary side. Correct, dear? Now we define the voltage regulation of transformer. Okay, there is a numerical is asked in your exam also. Voltage regulation. So like in alternator, same like in transformer also, there is a voltage regulation. What is basically it is? Actually, it is nothing but suppose you have a see, so this is your transformer. This is primary, this is secondary. Okay. Here, this is the rated voltage we apply here, V1. Okay, here V1. Then at a terminal, this secondary terminal, we take this is your load. Now maybe this is the load power factor cos phi 2. Okay. So here, see, suppose when we give here rated voltage at rated frequency, then if there is a switch, we put here direct method. Direct method means voltmeter method. So here we put a voltmeter. We have put a voltmeter, and there is a to connect this load. There is a switch. Suppose when first we close the switch, and we here there is a load. Okay, and we put also emitter here. Okay, emitter also. So this emitter is read the load current, correct? No? When the load is there, this measures the load current I2. When your transformer secondary taking the load current, full load current, then we note down this voltmeter reading. Okay, so this will give you V2. This is the load terminal load secondary terminal voltage at full load, full load terminal voltage. Then without changing the here input voltage and supply, we switch off this. Okay, we open this switch. Then it is no load. At no load, when the current becomes 0, and this volt is because here it is a E2. Now this terminal voltage here it is at V2. Okay. Now this current is 0, then this open terminal voltage is E2. So your voltmeter read the no load. This is secondary no load terminal voltage. Okay, no load terminal voltage, not at full load. This is at load, full load, and this is secondary no load terminal voltage. Okay, or it is no load voltage. Now, so this percentage voltage regulation is defined as nothing but it is the change in or variation in the output terminal voltage from no load to full load. With respect to, we take here reference value. Actually, because this is a change vary. This V2 is vary actually. So generally we calculate this voltage drop with respect to no load. Okay, V2 minus E2 minus V2 by V2 some. Okay, reference, or it is called up or down voltage regulation. Or generally we calculate with respect to full load terminal voltage into 100%. Okay, so this is the formula for voltage regulation. Okay, dear, this is your formula for voltage regulation, percentage voltage regulation. Correct? Okay, very simple. Now from this equivalent circuit parameter or your vector diagram, we can calculate the voltage regulation. Please, now today I explain this, very important. My dear, we draw a vector diagram, phasor diagram, it is. See, suppose this is as referred to, this circuit as referred to secondary side. Now this V2 we take as a reference vector V2. Okay. So suppose this is your here we take this is your V2. V2 voltage. Okay, dear, V2. This is your V2. 0 O center. Now, because there is a power factor, suppose it is at lagging power factor. We suppose this phi2 is lagging. So at lagging, your I2 load current I2 is lag. I2 is lag with phi2. Correct, my dear? Hello? It is important. Please see, this is your secondary terminal voltage. This is the current. Current here, this load current. This is your secondary load current. This I2. This is load current. It is lag with this because your power factor is lagging. Now, there is a, why this voltage is changed V2, E2 due to voltage drop in resistance and reactance. Here is a drop in this. Okay. So always, my dear, in resistance, voltage and this voltage drop in resistance and current, they are in phase. Okay. Phase in current. Current ke phase mein. Now the voltage drop here, please. Voltage drop here across this resistance or across this. So here, this is in phase with current, this voltage drop. It is parallel. Please always you draw this line with parallel to current because in phase with current. Okay. See, they are in this current and this resistive voltage, like it is I2 R02. Okay, there. It is, it is VR, correct? VR02 voltage across this resistance. It is in phase with current, current ke phase. But drop in reactance, it is perpendicular to this or perpendicular to current. In inductor when we write, see, this is the resistance, this is inductor like this. So now here we write here this V2 is like this is your resistive, this is your inductor, VL, this is VR, correct? Okay, so these two voltages are perpendicular to each other. Okay, so this inductive drop is here. It make a 90-degree angle here. Sorry. You make here 90-degree. Okay, this. So this is your I2X02. Okay, total drop in this reactance. Here and here. Drop, okay. Now, my dear, here you see in this diagram, this voltage plus this drop, it will give you total. What is here? It is E2 here. Correct, no? As refer to. Okay. E2 equals to E1 days. So this is E2 here. This is V2 here. As refer to secondary side. They are not come days. So see, this plus this voltage drop plus this will give you total. What is the potential here? Here E2. This will your E2. Okay, this will give you your E2. E2. Okay. Now I do simplify how we calculate E2. Okay. So actually you take a compass and you select the diameter of this length, E2 length, and you draw the circle. Okay, dear. Now we extend this. We extend this B. Okay, up to here. So now we can say this and this are same length, no? Correct? Okay, dear. Now we draw the perpendicular line here. Okay, my dear, this is the 90. Hello, these are parallel to this, no? So it means this is phi2. Now, my dear, here, now we are doing something. What is this length? This is V2, na? And this is, you take a vertical component, so it comes I2 R02 cos phi 2. Okay, dear? Okay? Now, similar to we can apply here, na? This is, this is 90. So this will come 90 minus phi 2. Then this is 90. This we calculate, then this angle are perpendicular. Now we draw the perpendicular line here. इस method में this portion we left, only this much is the error. Okay, now you take this is the right angle triangle. Actually, by some geometrical analysis, if we calculate, this angle is also come phi 2. Please remember. Okay. Okay. Now you take this vector. Yeah, this is a vector, Now, if you take this side is come cos theta. Hello, if you take this vector, this side it comes cos theta, but this side, when this become horizontal. Okay, my dear. So this length here, this much length, what is this length will come? Please remember, this come I to x02 sin phi 2. Please remember this length. And this portion we neglect, this much. So now we can calculate total E2 equals to V2 plus I2 R02 cos phi 2 plus I2 x02 sin phi 2. Any doubt, my dear? Okay, this is your. Now we calculate E2 minus V2. E2 minus V2, then this V2 is cancelled. Or you take this side, then it become minus. So this only we get R2 I2 R02 cos phi 2 I2 x02 sin phi 2. Okay, dear. Okay. And now if you calculate by voltage regulation, then it is divided by V2 also. Then for percentage, it comes per unit. Okay. Then percentage voltage regulation, it is multiplied by 100. Okay, dear. Easy. Means now this is the simple formula. With the equivalent circuit parameter, we can calculate the voltage regulation. Okay. Now this equation is for lagging power factor. Okay. Please remember, your voltage regulation is depends on, first is your R2 total equivalent resistance, total equivalent reactance. Then power factor also, cos phi 2 also. Now, suppose when phi 2 is 0 degree, means lagging, leading, or unity. So this is for lagging power factor. This equation is for lagging power factor. Okay, this is for lagging power factor. Okay, dear. Now, if leading power factor, only this is come minus, negative sign come. Please remember. This red is for, this come negative for leading power factor. If unity power factor, cos phi 2 is 1. it means phi 2 equals to 0 degree. Then sine phi 2 will be 0. This not entire thing 0 actually. At unit, now see, please remember, hello, if they ask the lagging power factor, please they asking at different power factor. So this equation for lagging power factor. For leading, please you write E2 equals to V2 since this minus. Here it is negative. Direct we write voltage regulation. Right. This become for lagging power factor PF. It is E2 minus V2 by V2. Then this equation it comes R02 cos phi 2 minus phi 2 x02 sin phi 2. Okay, dear. Divide. So this come negative. Okay. Now add unity power factor. Please add unity power factor means cos phi 2 equals to 1. Okay, dear. Actually, at unity power factor, this vector diagram, even in leading power factor, see, leading power factor, this current is lead. So this comes this side. Okay. Then this become negative. That's why. Okay. This is subtract. It comes opposite direction. That's why. Okay. But at unity power factor, see, you draw the vector diagram at unity, means this is your voltage. Okay, V2 suppose. V2. Now your current, I2 is in phase with this. Here it is. This is your I2. Because it is phi 2 is 0 degree. Now the resistive drop, it is in phase with current, means ये directly add हो जाएगा. That is I2 R02. It is add. And reactive drop, reactance 0 नहीं होगा. Reactive drop is perpendicular to this. So this is your due to resistance. This is your due to I2 X02. Okay. Then you calculate E2. This will be your E2 in this case. Okay. So now we can calculate. Now what is your E2? Here you calculate the value of E2. Okay. It is V2 plus I2 R02. Not cos by square plus I2 X02 whole square. Okay. By this is right angle triangle. That's got it, my dear. Okay. Then you apply in this formula E2 minus V2 by V2. Okay. Got it? It is very important. Now there was a question here. Hello. See here, why it is important to maintain the high efficiency, means if efficiency is high, hello, if efficiency high means losses are low. Losses are low means there is a saving of energy. Your electricity bill, your factory or plant is reduced. Correct? Second is when losses is high in transformer, due to low efficiency, then there is a I square R losses and heating. Actually losses appear in the transformer, either वो core loss है or either they are copper loss. They appear as a heat, no? The heat your transformer. जब heating होता है, so your life of your transformer means जो insulation है, like that is deteriorate. Your life is reduced. Okay. So there is a energy saving. Second is their life of equipment also. That's why we maintain the high efficiency. Why is the low value of voltage regulation? High value of voltage regulation means the drop, internal drop is high. Again, same thing. You know, the current is increase if voltage drop is there. And your motor terminals not get a rated voltage. See, in simple diagram, hello, why we maintain the low value of, see, this is your transformer, suppose. This is your secondary. Okay. Due to this, there is a percentage impedance means what? This is the your regulation. It represents your equivalent impedance. Due to this, there is a, this is your main switchboard, MSB, main switchboard. So now your motors are connected here, suppose. So see, if this internal voltage drop is more due to high value of voltage regulation, this motor terminal voltage, this motor does not get a rated voltage here because there is a drop here due to internal drop. Okay. So it is low value of voltage regulation is recommended. Okay, now see, due to voltage drop, internal voltage drop, again there is a current is high, then voltage profile is not good. Okay, correct now? That's why it is high value we recommend. Sorry, low value of voltage regulation and high value of efficiency. Now there is another question. This the magnetic leakage, how value is kept down? Meaning of vector diagram, this regulation of transformer due to magnetic leakage. So my dear, you have to draw this due to leakage flux. There is a leakage reactance. So you draw this equivalent circuit. Hello? You at least you draw this and you draw this vector diagram. Then you stabilize this relation of voltage regulation at least for lagging power factor, this part. Okay, उस क्वेश्चन के आंसर में आपको क्या क्या लिखना है, इतना पार्ट लिखना है. ओके, डियर, ड्यू टू लीकेज and initially you write what is the leakage flux, then leakage reactance. This one, second, question number second. Read this. इसको आप यहाँ जमक वेक्टर डायग्राम से एब्जॉर्ब कर सकते हैं. देखो कैसे आएगा. देखिए सपोज हम रेजिस्टेंस को नहीं है, वो केवल रिएक्टेंस की बात कर रहा है. लीकेज फ्लक्स मीन्स लीकेज रिएक्टेंस. ओके, ड्यू टू लीकेज फ्लक्स देयर इज अ लीकेज रिएक्टेंस मीन्स XX2 टोटल इक्विवेलेंट. लाइक देयर इज अ लीकेज फ्लक्स इन प्राइमरी. तो इनिशियली आपको एक लैंग्वेज लिखनी है. ड्यू टू देयर इज अ लीकेज फ्लक्स इन प्राइमरी एंड सेकेंडरी कोर. Due to franking effect, there is it is maximum flux is flow in the core, but some part is due to franking effect. There is a leakage flux. Due to leakage flux, there is a leakage reactance in primary and secondary winding. Okay, then you show like this is your vector equivalent circuit. No, this is the leakage reactance X1, X2. Their equivalent is X2. Now suppose if leakage flux is low, then your leakage drop is less. See, suppose अगर आपका leakage flux less रहेगा तो ये vector इतना बड़ा नहीं होगा, छोटा होगा. Suppose here only. Then see, your E2 is also reduced. Correct, no? If E2 is reduced, then your this voltage regulation is reduced, no? Okay, dear. Understand? Like here also, if you reduce the height of this, see, this is definitely it is great. E2 is greater than V2. Huh? If this part is we neglect the zero flux, means this part is zero. It means this vector is this. Means then in that case, E2 equals to, if we neglect na this resistance and reactance, then E2 equals to V2 only. Correct, na? Okay. So your regulation is 0% means. So it depends on power factor also. Yeah? Now there is a question. Now as referred to primary side also, sometimes they ask. So let us we formulate the primary side also. Okay. So actually in primary side same things only, but some changes are there. See here. This is as referred to. This is as refers to secondary side. This formula as refers to primary side. Then we take here primary voltage V1. No, this is V1 minus here this load across the load. This is V2 dash. V1 minus V2, or either you write E. Actually here this voltage is V1, or here we assume V1 equals to E1. So you write V1 minus E2 with respect to, actually we calculate with respect to V1 only. Okay, into 100. Now again here actually this power factor should be cos phi 1. But generally we take a phi 2 only we consider. Okay. And this is your total resistance and reactance. And here another thing, actually we take I1. Here actually here the drop is due to I2 dash, but in actual equation we write I1. We take I1. Okay. Okay. Here we also consider I1 equals to I2 dash. Okay, dear. So these two things you remember when we write this. Hello. So what is the main formula will come? This V1 minus V2 stays. Okay, as referred to primary side. Okay, voltage regulation. Same value will come, like I1 we take. I1 equals to R01 plus cos phi. Now not 1, it is only that power factor of transformer is given. Either you write here phi 1, basically it is phi cos phi 1, but we take here phi 2 value same. Plus I1 x0 1 sin phi 2 again. Okay, this correct. Divide by V1. Please remember V1 into 100 if you calculate as a percentage. Okay, dear. This is the voltage regulation as referred to primary side. So there was a question also in your exam which was asked. Large question. Okay. Copy किधर किया था question ये रहा. This one recently asked. Part B. This is a big question. Following result were obtained. Actually, this parameter, equivalent circuit parameter, X X01, R01, huh? This we calculate Z01, and now X01 we can calculate total, na, this Z01 square minus R01 ka square, like this, because this is an impedance triangle, na, hello, suppose this is your impedance triangle. This is the total resistance as referred to primary side. This is total resistance reactance as referred to primary side. This is your impedance, total equivalent impedance Z01. Then this is phi 1, or here it is also in formula. Actually, you write phi 1. Okay, phi 1. Okay, please. Now, so this parameter we can calculate from equivalent, short circuit and open circuit test. So it says a result on 50 kVA. There is a 50 kVA transformer. We conduct a open circuit. So in open circuit we apply the rated voltage. Then we get a secondary voltage. So this is your rated values. This is V1, my dear. Hello. This is your V1. This is your V2. Okay. Or E1 or it is E2. Okay. Now primary power factor. Sorry, primary power. This is your power. Means this much watt. On open circuit test, na, that is W naught, power input. That is V1 I naught cos phi naught. That is 430 watt. Then it is under short circuit, your primary voltage is, now on short circuit we apply the reduced voltage. This is your reduced voltage. Okay. Then current is this. Now in short circuit, current is flow. We measure the source. So this is your actually VSC. We called it a short circuit current, means voltage during short circuit test. This is your short circuit current, which is measured, and this is the short circuit power, SC. Okay. So by using this parameter, hello, this VSC by ISC, hello, this give you your Z equivalent impedance. Okay. ISC by VSC by ISC. Yeah? Because this is the ratio is fixed, constant. That's why. And second is losses during short circuit, total equivalent resistance R01. That is ISC. Okay. Equals to how much it is given? What? 525. Now from this you calculate R01. That is 525. Means it is WSC. Okay, power. Divide by ISC square. If you divide by this ISC square, the current is given 15.3. Then you calculate this ohm. Then you calculate X01 equals to Z01 square minus R01 square. So now you calculate this power, Okay. You calculate this, hello? You got this parameter. This we calculate, we require this and this. Okay? Correct, no? Now we require a power factor also. We apply the red shade, no. Power factor they are given. Now they ask, hello, efficiency at full load and half load at point power factor. So you know, for efficiency you calculate the total losses. So what is the losses in transformer? You know, no load open circuit test will give you core loss. जो W naught है, that is your 430 is iron loss. That is iron loss. Okay. And your this short circuit में this will give your power losses. Okay. Or either you calculate a total power loss. And you know, in short circuit test we measure the copper loss. So this is iron loss and your copper loss equals to, that is 15.3. So it is 5. to 5 watt. So this is your losses are given. Then we can calculate na efficiency. Now what is the output? 58.7 power factor. Then 50 into 0.7. It will be your transformer output. Okay, in kilowatt. Then input. This is your output. Input we calculate. Add the total losses. Then efficiency, and at half load you take a half, means 25 kVA. So first part we can solve. Second is voltage regulation for 0.8 power at lagging and leading. So my dear, you use this formula as referred to primary side. Okay. Hello. Yes. This
in case of half, these losses are also going to reduce now 1.4.
Which one?
Is copper losses?
No, losses will not reduce. Copper loss are reduced. They become 1/4. But iron losses are fixed.
Yes.
Yeah. Then this voltage regulation you can calculate. Lagging and leading. Only leading mein there is a minus sign is come. Okay. Then secondary terminal voltage. If you have a voltage regulation, means this much percentage drop. So you have to subtract the percentage drop from your terminal voltage. Like this is your secondary voltage. Hello. Actually now we consider this 415 is a E2. Okay. Then he is asking V2. V2 equals to E2 into your percentage voltage regulation drop. This drop we have to subtract from your E1. Okay, what is your B2 actually? B2 is output terminal voltage, that is E2 minus percentage drop here, voltage regulation. Okay, percentage voltage regulation. This E2 minus this drop. Then you get a V2. Okay. So this very simple, both. Tomorrow we discuss, we solve this. If you don't get it, you try yourself. Okay, correct?
सेकंड वाला पार्ट एक बार फिर से बताइएगा.
Second, actually when we calculate the voltage regulations, correct? In this question part 2 mein we calculate a voltage regulation. Okay, so we get a like suppose 5% you get 5% voltage regulation. यहाँ पे लेगिंग पे पॉजिटिव आएगी. इन लीडिंग ना इट इज मे बी -2% सपोज नेगेटिव आती है. ओके, लीडिंग पे. करेक्ट. देन ही इज आस्किंग सेकेंडरी टर्मिनल वोल्टेज. तो योर V2 equals to E2 is 415. It means there is a 5% drop with respect to E2. 415 into 0.2 means it is divided by 100. So just 0.05. 0.05 you multiply and subtract. So what is your terminal voltage? My dear, your this voltage is come 334. So what it saying? It means suppose this is your transformer. When there is a load, then this V2 is here, and E2 be assume like it is 415 volts. Suppose then V2 become like 394 volt. Or if that's why we put na like here the secondary no load voltage we put 433 volt, and so that after the drop we get here terminal voltage 415 volt. Okay. So when we calculate na this terminal voltage, this voltage we assume as a induced voltage. Okay, this. Then there is a percentage drop. Correct. Voltage regulation is what? Actually, it is a percentage voltage drop. Okay. Got it? So when you get the value of percentage voltage regulation, then you calculate the terminal voltage. Just you subtract the percentage drop from your terminal voltage. Okay? Very simple. Okay, good night.
ओके सर, गुड नाइट सर। इसका क्वेश्चन का आंसर आप
कौन सा क्वेश्चन?
सर सेम जो ये अभी नवंबर में आया था, ये 50 केवी ट्रांसफार्मर का।
ये डाला हुआ तो है उसमें, और हम कल इसको सॉल्व करेंगे ना।
ओके सर, ओके।
आंसर के लिए आप तकलीफ मत करो, ये सेम क्वेश्चन नहीं आने वाला, आप सीखो उसको करना कैसे। नया क्वेश्चन आ गया तो हाउ यू टू डू। ओके, आवर अप्रोच शुड बी फॉर न्यू क्वेश्चन। आप ये 5 क्वेश्चन रटने से भी फायदा नहीं है। नाउ इफ दे आस्क द न्यू क्वेश्चन, you should know the method. Okay. Good night.
Thank you, sir.
Right.